Hello everyone, my name is Srinidhi Parshi and I'm going to be presenting on the point processes applications in gamma ray bursts and pulsar astronomy. This presentation is part of the data science application of the course ECE 6397 State Space Estimation with Physiological Applications. This presentation will have the following outline: an introduction about the topic, methods of the point processes, discussion of their application, and possible future direction and conclusions. I have also added a reference slide about the sources of the material used in this presentation. As an introduction, let us proceed about discussing the manifold applications of point processes in astronomy. Solar flares are violent bursts from the sun's atmosphere, which can be looked at as spike times. The space debris that revolves around our planet Earth can be looked at as a counting process. The two cases we will be looking into in depth in this presentation are the GRBs or the gamma ray bursts and the pulsars, which can be characterized as wait time distributions or increments. Let us begin with the gamma ray bursts. Gamma ray bursts are extremely energetic explosions that have been observed in distant galaxies. The intense radiation of most GRBs is thought to be released during a supernova or a superluminous supernova when a high mass star implodes to form a neutron star or a black hole. One of the main reasons for studying gamma ray bursts is that they are extremely dangerous to life on Earth. If a gamma ray burst occurred within the Milky Way galaxy, it could wreak havoc if it were pointed directly at Earth from thousands of light years away. In fact, a GRB has been suggested as a possible cause of the Ordovician extinction 450 million years ago. A gamma ray bursts have enough energy to strip away Earth's ozone layer and in some cases the atmosphere, making life very difficult to exist. Due to this reason, only 10% of the overall galaxies in the universe have been postulated to be suitable for life. We come to the second topic of our discussion, that is a pulsar. Pulsars are actually a remnant of a supernova explosion, that is what is remained after the star implodes. A pulsar is a highly magnetized rotating neutron star that emits a beam of electromagnetic radiation, and by precisely measuring the timing of such pulses, astronomers can use pulsars for unique experiments at the frontiers of modern physics. One of the most studied pulsars is in the Crab Nebula. Pulsars are very interesting astronomical objects. Their research is at the forefront of gravitational wave detection. In fact, the research on pulsars in binary star systems with other neutron stars and with, in another case, a pulsar, offer the best test yet of general relativity in very strong gravity. The top right image depicts the NASA's Voyager Golden Disk. In it, the bottom left image depicts the location of Earth with respect to different pulsars in the Milky Way. This shows that pulsars can also be used as a sort of interstellar GPS. Now, let us proceed to the application of different point processes on pulsars and gamma ray bursts. The radio bursts from pulsars can be modeled as Poisson distributions. Specifically, the wait times between the pulses form a Poisson process. So we first collect the data on the timing of the great giant pulses from, for example, say a Crab Nebula pulsar, and then we assume that nt is a number of giant pulses in a time period of length t is a Poisson process with a constant rate lambda. There are papers existing that show that these pulses are very well modeled by a Poisson processes. They also apply the maximum likelihood estimation theory to estimate the value of lambda. In the second case, the gamma ray burst can either be modeled as a two-dimensional spatial Poisson process or combined with the X-rays for prior GRB detection. There is compelling evidence that X-ray flares are linked to the prompt gamma ray bursts. The waiting time distribution of pulses and flares can be the manifestation of a common time-dependent Poisson process. And this has been shown to be modeled as a Poisson process with the same maximum likelihood estimation to estimate the model parameters. Let us now revise the methods that have been taught in the class. A Poisson process is a probabilistic model for random scatterings of points on some space X. And the simplest and most ubiquitous example of this point process is the Poisson point process. So we can model the number of spikes that have been occurred in specific time intervals of t2 to t1 in this format where lambda is a model parameter. Maximum likelihood estimations, or the likelihood function, provide an objective means of assessing the information in a sample of data about the model parameter. Most commonly, the model parameter that has to be estimated would be lambda. The Kolmogorov-Smirnov plots, or the KS plots, are statistics that quantify a distance between the empirical distribution and the cumulative distribution of the sample. Now, let us look at the actual equations that have been used to model and apply to the gamma ray bursts example. One possible way of gamma ray modeling is to look at the gamma and the X-rays that are resultants of the GRBs. So they can be modeled as several different functions, several different probability functions, and incorporating these GRB values, you can add other parameters such as outlier flares or sudden rate increases, etc. And finally, to estimate the alpha and the beta parameters as given in the source material, we can use the maximum likelihood estimation. The results of these applications to the gamma ray bursts can be seen in the following figures. They have been extracted from the source material, and we can see the probability distributions of the model versus the actual distribution that has been observed. And in both cases, it has been pretty close to the observed value. So it in turn implies that the Poisson processes is the correct way of modeling for these gamma ray flares. Let us now take a look at the applications to the pulsar astronomy side. We can see in the image that the pulses can be modeled as increasing spike times, and there can be other parameters in a similar way to the GRB example that have been included in the pulsar example, and they can also be estimated using the maximum likelihood estimation. The source material also goes through these equations in depth, and I would like to reference you to that if you are interested in more reading. The possible future directions and conclusions of this topic can be that the most goodness of fit models in pulsar astronomy still make use of rudimentary techniques like least square estimation, etc. A maximum likelihood estimate for parameters would more likely improve the model. Multivariate point processes can also be used to model simultaneous events like GRBs, collisions, supernova, etc. And we can also probably include the KS plots to determine the confidence levels of the model as compared with the original observations, etc. These are the references that have been used in the following slide, in all of the slides that have been presented. The pictures and other media can have the source material that were mentioned at the bottom of the specific slides. Thank you.